Picture this. It's a clear night. You step outside, look up at the sky, and instead of one moon hanging overhead, there are two, side by side, glowing, slowly drifting apart. It sounds like something out of a science fiction movie. But what if it wasn't? What if right now some massive collision struck the moon and cracked it in two, splitting our only natural satellite into a pair of smaller worlds? What would happen to Earth? What would happen to the oceans, to our seasons, to life itself? The answer is far stranger and far more fascinating than you might expect. Because it turns out the moon does so much more for our planet than just light up the night sky. And when you understand what it actually does, the idea of losing it or splitting it becomes genuinely alarming. Let's find out exactly what would happen. Before we explore the consequences, let's set the scene. How would the moon actually split in two? The most likely scenario would be a catastrophic impact, a large asteroid or comet slamming into the moon at tremendous speed. The moon has no atmosphere to burn up incoming objects, so it's completely exposed to whatever the solar system throws at it. We can already see the evidence of that. The moon's surface is covered in craters, billions of years of cosmic bombardment recorded in stone. A large enough impactor could fracture the moon along its core, sending two massive chunks drifting apart from each other. Initially, they wouldn't go far. Earth's gravity would hold them close. But over time, and we're talking millions of years, the two halves would slowly pull apart, each settling into its own orbit around Earth. Here's something wild. Scientists actually believe Earth may have already been through something like this. Research published in the journal Nature suggests that roughly 4.5 billion years ago, Earth had not one but two moons. A smaller companion moon shared our sky for about 80 million years before being pulled into a slow collision with the larger one, what scientists call the Big Splat. That collision is now thought to explain why the far side of the moon looks so dramatically different from the side we see, with its thick crust and mountainous terrain. In other words, the moon we look at tonight may literally be made of two moons merged together. So this isn't pure fantasy. It's happened before. Now let's ask, what if it happened again? The moment the moon splits, the first thing people on Earth would notice is the sky. A fresh split would be dramatic. The collision itself, assuming it was a large impact, would release enormous energy. Both chunks would likely be partially molten and glowing. For weeks or even months, anyone looking up at night wouldn't see a gentle silver moon. They'd see two bright, irregular volcanic objects hanging in the sky, cracked and smoldering like embers. The debris field would be significant too. Billions of rocks and boulders, sent flying in all directions by the impact, would enter Earth's vicinity. Some would be captured into orbit. Some would fall. Meteor showers would become a near-constant feature of the night sky, and not the gentle kind. Large fragments could impact the Earth's surface, triggering earthquakes, wildfires, and tsunamis on a regional or even global scale. But that's the dramatic opening chapter. The more profound and lasting changes would come later, and they'd be written into the very rhythms of the planet. Let's talk about tides, because this is where things get genuinely fascinating. Right now, the moon's gravitational pull causes the oceans to bulge outward on both the side of Earth facing the moon and the side facing away. These bulges are our high tides. As Earth rotates, different coastlines pass through those bulges, giving us our familiar cycle of roughly 2 high tides and 2 low tides each day. It's predictable, it's reliable, and an enormous amount of life on Earth, from microscopic plankton to entire coastal ecosystems, has evolved around that rhythm. Now split the moon in two. Each half would be roughly half the mass of the original moon. And here's the key: gravitational force scales with mass. So each half would pull on the oceans with significantly less force than the moon does today. The immediate result would be weaker, smaller tides. But it gets more complicated. Two moons orbiting at different distances and speeds would create competing gravitational tugs. Instead of the clean, predictable tidal pattern we have now, coastlines would experience chaotic, irregular tides, sometimes amplified when both moons aligned, sometimes dampened when they pulled in opposite directions. For coastal marine life, this would be catastrophic. Tidal zones, those areas of beach that are alternately submerged and exposed, are some of the most biodiverse environments on Earth. Countless species depend on knowing exactly when the tide comes in and when it goes out. Disrupt that, and you disrupt food chains, breeding cycles, and entire ecosystems. Now here's where the story gets really deep, and this is probably the most underappreciated thing about our moon. Earth's axis is tilted at about 23.5 degrees. That tilt is the reason we have seasons. It is why summer days are long and warm and winter days are short and cold. It's why we have the climate patterns, the rainfall cycles, and the agricultural conditions that make this planet livable. And that tilt is remarkably stable. It barely wobbles. It varies only between about 22 and 24.5 degrees over long cycles. That stability is no accident. It's the moon holding us steady. The moon's gravity acts like a giant gyroscopic anchor on Earth's axis. Without it, the gravitational influences of other planets, Jupiter in particular, which is enormous, would tug at Earth's tilt chaotically. Scientific research published in the journal Nature showed that without the moon, Earth's axial tilt could swing wildly from near 0 degrees all the way up to 85 degrees. That's not a different season, that's a completely different planet. Now, splitting the moon in two wouldn't eliminate this stabilizing effect overnight, but it would weaken it. Two smaller moons with less combined mass than the original would exert less of that stabilizing gravitational torque. Over thousands and millions of years, Earth's axial tilt could start to drift in ways it doesn't today. Seasons would become less predictable. Climate patterns would start to shift in ways no weather model could forecast. Here's a surprising one that most people never think about. The moon is actually responsible for the length of our day. Right now, the moon is very slowly breaking Earth's rotation through tidal friction. As the ocean bulges are dragged by Earth's spin, they transfer rotational energy from Earth to the moon. The result? Earth's days are getting longer, by about 2.3 milliseconds every century, and the moon is drifting away from us at about 3.8 centimeters per year. It sounds tiny, but over geological time it's enormous. Around 70 million years ago, during the age of the dinosaurs, a day on Earth lasted just 23.5 hours. Go back 1.4 billion years, and a day was only about 18 hours long. So what happens if the moon splits? Two smaller moons exerting weaker tidal forces would slow this breaking effect. Earth might stabilize its rotation, or even spin slightly faster over geological timescales. Days could end up being fractionally shorter than they would have been. Ocean currents, wind patterns, and climate systems that all depend on the speed of Earth's rotation would adjust accordingly. Subtly, slowly, but persistently. The effects on living things would extend far beyond coastal ecosystems. Many animals use the moon as a navigation tool. Sea turtles use it to find beaches. Birds use it during night migration. Certain coral species synchronize their mass spawning events with the full moon, timing their reproduction to a precise lunar signal. Two moons with irregular cycles would throw these biological rhythms into confusion. Nocturnal animals would face a different kind of disruption. With two reflective bodies in the sky instead of one, nights would on average be significantly brighter. Animals that depend on darkness to hunt or hide would be far more exposed. Evolutionary pressure across thousands of species would shift overnight, quite literally. And there's a more fundamental question lurking beneath all of this. Life on Earth didn't just evolve alongside the moon. It evolved because of it. The stable tides created by the moon billions of years ago are thought to have played a critical role in driving early life from the ocean to the land. The rhythmic exposure and submersion of tidal pools may have been the very engine that produced the first complex organisms. Without the moon's influence, life on Earth might never have reached the complexity it has today. Weaken that influence, fracture it, split it apart, and you don't just disrupt the present. You cast a shadow over what life on Earth could become. So let's bring this all together. If the moon split in two, Earth would face an immediate wave of meteor impacts and chaos in the sky. Our tides would become weaker and unpredictable, devastating coastal ecosystems and disrupting human civilization. Over time, the stabilizing influence on Earth's axial tilt would weaken, potentially setting the planet on a path of increasingly chaotic seasons and climate shifts. Earth's days might subtly change. Entire categories of animal behavior tied to the lunar cycle would be disrupted, and the very conditions that made complex life possible in the first place would be under threat. But here's the truly mind-bending thought to leave you with. This may have already happened, not the splitting, but the ancient story of two moons in our sky. Scientists believe that 4.5 billion years ago, Earth had two moons for tens of millions of years. They shared our sky. They shaped our early world. And then, drawn together by gravity in a slow-motion collision, they merged, leaving us with the single, scarred, asymmetric moon we have today. The moon you see tonight isn't just a moon. It might be the survivor of a two-moon system that shaped the very conditions for life on Earth. Next time you look up at it, you might see it a little differently.